So the dimension of a vector space V is the number of elements in any basis of V. And that at first blush looks like it might not be a well-defined or clear idea, because what if you produce a basis and I produce a basis and they have a different number of elements? Well, there's actually a theorem, and it's sort of a deep theorem, but we won't get into it. It says that any two bases for V will have the same number of elements. So this idea in the definition that it's the number of elements in any basis, that is actually a well-defined idea. There's no vagueness or arbitrariness to it. And I should mention also that there's one vector space that doesn't have a basis. There's only one, and that's the silly one, so the trivial one. So if we've got the trivial vector space, then we define the dimension of V to be just just 0. So that's the only vector space with dimension 0. If we look at other more common examples, so how about Rn? Well, you know, or you probably guess, that the dimension of Rn is n. That just makes sense. And of course you're right. But how would you actually prove it? Well, the way that you find or compute the dimension of a vector space is by exhibiting a basis and count the number of things in it. So let me write that down. So to compute the dimension of V, write down or exhibit a basis of that vector space then count its elements. Okay, so we know that for Rn, the standard basis is the one comprised of the columns of the n-dimensional identity matrix. So it's the one that has 1 and then a bunch of zeros, and then 0, 1 and a bunch of zeros, and so forth, until you get to the one that's all zeros except for the very last entry. And if you count these, well, it's the number of pivots in the n-dimensional identity matrix. So there are n elements in that basis, and as a consequence, we can conclude officially and from the definition that the dimension of Rn is indeed n. Okay, so what about looking for some other vector space that's maybe not quite as simple? Let's say the 2x2 matrices. So a standard basis for the 2x2 matrices, well, we look at A, B, C, D, our standard generic element of M2, and see that it can be written as a linear combination of these 4 matrices that have just a single non-zero element in each one. And so if we look at this collection of these 4 matrices that we have right here, you can see readily, well, this equation shows that they form a spanning set for M2. As for linear independence, I'm not going to go through the full proof. I claim that this is clear from inspection, because so for this first one, for example, it's the only one that has a non-zero entry in the 1, 1 position. So no matter how many of these other 3 you add together, you're only ever going to have zeros in each of these 3 positions, and adding together zeros will never give you a 1. So A is definitely not redundant. And the same argument can be made, symmetric argument can be made for each of the other four. And so as a consequence, I would say that it's a linearly independent set. Okay, so putting that together, we have that we've located a basis and once you've verified that this is a basis, then you can conclude that the dimension of M2 is 4 because there are 4 things in the basis. What about if you didn't take all of M2 but you just took the symmetric subspace? So all those elements of M2 that are symmetric or equal to their own transpose. Well, then we would have, let's see, so our generic element in this case is something that looks like A, B, B, C. And so a spanning set for S2 is, and I'm calling it S, maybe I'll call it B because it's going to turn out to be a basis. So our so if we look at 1, and 0, 1, 1, 0, and 0, 0, 0, 1, this one spans S2, and we can see that that's exactly the content of this equation that I have right here. Okay, so that's definitely a spanning set. To see that it's linearly independent, well, okay, instead of doing what we did in the last one, let's do this one rigorously. So I can, what if I take these 3 matrices over here and write them as columns in a matrix? So I have 1, 0, 0, 0, and 0, 1, 1, 0, and 0, 0, 0, 1. And I row reduce. And I find that I have 3 pivots. And so since I have a pivot in each column, that means that that this is a linearly independent set. Whoops. And so together, based on the fact that it's independent and that it's spanning, I know that I have a basis. And since there's 3 things in there, I know that the dimension is 3. And for those of you who are wondering, hey, wait a minute, what was up with that? Just write those matrices in as a basis with some order. So I put, like the A11 entry in the first one, and A12, and A21, and A22. What allows me to do that? Well, I'm just repeating the same thing that I did in a previous example, but I just took a shortcut and jumped straight to the end.